is a professor at Princeton at Orphy, and he's going to tell us what has mean field theory ever done for us, mean field games ever done for us.
So oops, I promise that I will stay on time. So the reason of the title is due to the fact that the original publications on the subject appeared in 2006. We are 2013, and my contention was that there was not as much publication as what we should have seen over the last few years on this topic. And this is because, of course, I found the topic extremely exciting, extremely innovative, and rich for applications all over, not only in economics, but in social science, in physics, and in mathematics. So as I said, the field, in a sense, started in 2006, and independently by two groups of people, Jean-Michel Lasserie and Pierre-Louis Lyons, and a few collaborators like Olivier Guérin, etc. And they have this paper in the Japanese Journal of Math, where they describe the problem, and it's very well written, beautifully explained. And then basically everything went down from that point, because they wrote basically business prospectus rather than academic papers, and announced a lot of results, but didn't publish any proof whatsoever of this result, and that's that was pretty upsetting to me. They used the terminology mean field games, and that stuck. This terminology remained.
Do you understand why they did that?
This is taped, so maybe we can have private conversation if you want, and I can, or if you add to the bottle of Côte du Rhône, or Châteauneuf-du-Pape, maybe I can tell you even more.
This panel will not be taken. This discussion afterwards will not be taken.
So independently and simultaneously, a group of Canadian, Peter Keynes, Minnie Huang, and Roland Malamé, and a few other one, Rene, etc., wrote a paper, and 2 papers, and 3 papers, and 10 papers, and 100 papers, basically on the same subject with the same strategy, the same results. They call that Nash certainty equivalent, and the name didn't stick. Basically, themselves, they tried to stick to this name for a while, but then they gave up, and now they call what they do mean field game as well, even though they tried very hard for a while to differentiate themselves from Lyons and Lasserie. They published many papers, but from a mathematical point of view, I found this paper relatively frustrating, because basically they describe the method very well, and each time they describe a step, they articulate an assumption under which this step is valid. And another step, another assumption, another step, another assumption. And in the end, the existence theorem is of the form, if constant C1 appearing in page 12 times constant C2 appearing in page 14 divided by constant is smaller than 1, then there is existence and uniqueness. So that's in a sense why I was frustrated. But these 2 papers, these original papers, are absolutely magnificent, and I would encourage anyone who wants to learn to go to the original paper. And everything is described except basically the mathematical theory and existence result. They went on to describe a lot of applications, but the mathematics is a little bit frustrating. So the way I want to see these problems, and this is not necessarily the best way to look at it, but this is the way I got into it, and I tried to learn the subject and study it, is to think of large stochastic differential games. So we're going to talk about dynamic games. It's not a one period. It's not a static problem. It's repeated games, like we say in game theory, but we'll have time to be continuous and large in the senses with the large number of players. I don't see him, but Alex this morning talked about a mathematical model, which is still here, where the number of players is a continuum, and each player basically is a point in the unit interval. And in a sense, mean field game in a certain limit can provide a rigorous mathematical limiting framework to understand these games as finitely many player games. As I said, we may not want to care about it, but that's the way I want to look at it. So typically, I'm going to assume that we have a number, capital N of players. Each player has, a private state, which I'm going to denote by xi of t at time t, which evolves according to a certain dynamics. And, according to my bias, I'm going to take a Ito diffusion, but we could add the jump if you want. That's not too important. I'm going to make I'm not going to be very precise about mathematical theorem in this short presentation anyway. So what I want to emphasize is that the evolution of the state of these n players depends, the evolution of the private state of player I depend upon xi, and then upon this baby mu n t bar, which is the empirical distribution of the other states. So in other words, each player, each agent interact with some form of average of the other one. It doesn't distinguishes among the different other players. It sees a field of other players. Same thing in the volatility. And each player, we're going to have to solve an optimization problem. So we're really doing game theory. We're going to solve an optimization problem. Each player has an objective function. And these objective functions will, again, the objective function of player I will contain its own private state, the distribution of the states of the other player, and even possibly the distribution of the controls, the action of the other player. So this is the general, it's not the most general because I'm going to add some twist to it a little bit later, but this is typically the type of model that I want to look at. Many people trying to optimize, maximize, minimize their own personal objective functions, and they belong to a large system which evolves according to equation dynamics, which are influenced by their own individual action and the average field, both of states and of actions. Say that again. So this is the Dirac measure. So this is the point. But you can think of very simple examples. Very simple example of this form. In other words, dxi is a function of xi and the average of the other xi, or the average of a function. So mean variance would fit perfectly in this sort of thing. So the mean variance problem will fit perfectly in this sort of problem. You can be a little bit more complicated, and these are the most simplistic type of interaction that you may want to consider. But you can also, and we'll do that in a minute, consider interaction where you look at not only the distribution, but the quantile of the distribution. I want to compare what I'm doing to the 95 percentile of the distribution. And this mathematically is much more difficult because, quantile of a measure is not smooth. The function of a measure is difficult to have a smooth function of measures, but functions of quantiles of measure is even a little bit more difficult to handle mathematically. Okay? But the idea is that, we have this large game, and technically, computationally, these are very difficult to solve. So the philosophy we're going to try to use, and this is the idea of mean field game, which I think is absolutely beautiful, is to use idea from statistical mechanics to try to basically take a limit, look at effective equations in a large n regimes, And from this effective equation, which have nothing to do with the reality of the n players, so I have 50 agents behaving in a community. So 50 is not a continuum, but I'm going to use the equations, the effective equation that I'm going to compute in the continuum to try to go back down to an n-player game. And, well, I'm going to lose something, and possibly instead of having an exact Nash equilibrium, I will settle for an epsilon Nash equilibrium. Okay? So the strategy, even though this last part is completely forgotten in many of the papers that have been written, but the strategy, the way I see it, is that I want to solve for a Nash equilibrium in a finite player game. I'm going to invent an effective problems, okay? And I call it problem, and I don't call it game anymore, because it's not going to be a game, in fact. It's called mean field game, but it's not going to be a game. So I'm going to extract a limiting regime in which I set up a problem, I solve this problem, and hopefully from the solution of this problem, I can find a way to identify strategy such that if the n player of the finitely many player game use this strategy, the system will end up in an approximate equilibrium. Okay, so that's the idea. So since I'm already running late, I'm going to jump a little bit. So what this is the strategy as I define it, and the issue will be that when I ask the agent, the players, to use this strategy, will my system be in equilibrium, and what kind of equilibrium? And in fact, if I do not pay attention carefully to what I'm doing, I may think that I'm going to get a Nash equilibrium, and I may get some different type of equilibrium. And this was something that slowed me for at least 2 years in understanding what these things are, because in fact you can miss the target and manipulate something different, which I think is also very interesting mathematically, as long as you understand that it is different, which I didn't for a while.
Clarifying question. Can you just go back one slide, just to where you were? It seems that you're now writing out my action at time at player I as a function of t and xi of t.
Yes. So
shouldn't it be of the x of t as of all the other guys?
So if I want to look for strategy of this form, if I want to tell a player, look only at your belly button, look only at your own private state, don't look at the other one, and just make your decision, take your action on the basis of only this knowledge, it's clear that I'm not going to be able to get a real Nash equilibrium. I'm going to have to lose something, because it's, the states of the system involves not only my state and the other guy's states, and then the distribution. So I'm losing something. But the beauty is that will be enough to get epsilon Nash equilibrium, and we have a rate of convergence towards zero of this error epsilon n. Okay, so this is a very good remark. In other words, I'm rushing, but indeed we're going to be able to find strategy that are very strange and restrictive, but I'm not going to get to a Nash equilibrium. Okay, so I'm going to have an approximate Nash equilibrium. So it's true that if we relax the strict inequality, and we willing to take the inequality at epsilon, we can find many things. But here, we're going to be able to identify strategy of this form. Hans, you had a question? So the information is going to be contained in this function phi. This function phi is going to come from the solution of the effective equation in the limit. And in this limit, the distribution and the features, the dynamics will be capturing this.
Solution of the problem, in some sense.
Yeah. But still, the strategy, I'm going to be able to tell the people, hey, look only at your belly button. Don't look at anybody else, and use this strategy, and the system will be more or less in equilibrium. So it's pretty strong a statement. And it's true, it works. Okay, so as I said, this was originally proposed, this strategy by Lafley and Lyons and Kane, Malamé and Huang. So the idea is that because of the symmetry that there is in the problem, because of this exchangeability in the problem, we expect that when n is large, there'll be a law of large number or de Finetti type of theorem, which are going to make things converge, okay? In particular, the empirical distribution defining the interactions between the different players are going to converge. In the simplest case, they're going to converge to something deterministic. In the sophisticated case that hopefully I'll try to mention at least, they will converge to random measures, but at least they'll converge to something. And so by taking a step ahead and saying, okay, so I'm going to get to the limit when I'm going to work with this effective equation, I'm going to take this distribution to be frozen, fixed. Because in the limit, when n is very large, this has to be fixed, okay? So this is the strategy of mean field games. So the mean field game problem is not a game, okay? So you fix a deterministic flow of measures. As I said, in the most challenging problem these days, this thing will have to be a stochastic process of measure, a measured value stochastic process. Once this thing is fixed, now you take this famous representative player. So you imagine that you have this representative player. So this is what you get in the infinity. And you solve a plain stochastic control problem. So it's not a game anymore. It's a stochastic control. And you, in a sense, you compete against the flux, against the bath, the measure mu t. Okay? And so you solve a stochastic control problem. Okay? So if you can solve this stochastic control problem, you're going to have a distribution for the optimal xt, the optimal state. And now what you're going to demand is that the distribution of this thing be the measure that you started from. This fixed point argument is what makes things very difficult mathematically, especially when the flow of measure is random. But this is why it is a Nash equilibrium. It is a Nash equilibrium because a Nash equilibrium is simply looking at the best response of each player and looking for a fixed point of this map. This is, in a sense, summarizing all the players in one, but this is the strategy of finding a Nash equilibrium, but there is no game anymore. It's just a control problem and a fixed point, okay? And as I said, if you can solve this limiting problem, you can go back, and this is because of results from the propagation of chaos theory and the theory of the McKean-Vlasov equation, which tells you that eventually, in the situation that I presented, when there is no common noise, all the players are going to basically behave independently of each other in the limit n tends to infinity, and the state is going to evolve according to a very specific dynamics of the McKean-Vlasov type. And this is why, using this approximation by an infinite product, you're going to be able to get back to finitely many player and have a rate of convergence, et cetera, et cetera. Okay? So now I'm going to say in a few minutes that I've left, I'm going to mention a few applications. So these things, because so let me give you now a hint on how this is done. So people like Lastry and Lyons, and even Cain Malamé, you have a control problem. I write down HJB. I've done that all of my life, writing a HJB equation, nonlinear PDE, and I'll solve it. Or I have a fixed point here, but this is simply the distribution of something which looks like a Markov process at time t. So I have a Kolmogorov equation. So they write down an HJB equation, they write down a Kolmogorov equation, and they try to see if they can solve them simultaneously. Solving them simultaneously, meaning that they can solve this fixed point. The major difficulty here, I'll say it in one word, is that the HJB equation is backward in time, and the Kolmogorov equation is forward in time. Each equation on its own could be very easily solved, but solving them because of you have the two direction of time, it's difficult. So what I did with a few collaborators and students is look at, and I'm not going to mention that here, is try to look at all this problem, but from a probabilistic point of view and not from a PDE point of view, and using theory like the stochastic maximum principle to revisit this problem and try to produce solution to this problem. But the difficulty remained the same. The two colliding directions of time. Okay, whether it's by solving forward, backward SDE or solving PDE where the time is works in two directions. So I'm going to say just a few words about a lot of application. In economics, we're talking about herding. In population biology, we can talk about flocking. Or if you look at school of fish, this is beautiful. And so you can write an equation where you have the position is just the integral of the velocity. The velocity is given by something that control. Let's say each bird's control is velocity. And then you're going to minimize, or you don't want to spend too much energy. So you're going to minimize the kinetic energy. And then you may want to be like the other birds. You may want to be like the other birds because you don't want to be the victim of a predator, or because you want to fit in, like the teenagers. Okay, so you write a game, and this was written by Nurian Kane Ismailame, I believe, but unfortunately, convexity assumption are not satisfied here, and they couldn't solve it. But I don't know if you can hear. So mean field game could be used to try to explain these beautiful images. I don't know if mean field game could help with the music, but this music is beautiful. Oh, I'm saved by the fact that my laptop crashed. The video is a little bit longer, but it crashed, so that's okay because I'm running late. So this particular model, which I had the equation for x, for the position, the velocity, and then I had a noise, but there was one noise per bird. So it's like a noise attached to the wing of the birds. In this type of problem, there is definitely a noise which is due to the environment. Okay, so like you have transport property in random flows. So this is the typical example where you want to add a random environment and try to see how this random environment will affect the equilibrium, if any. Okay, even the simplest possible, what we call the common noise, adding. So you have here the idiosyncratic noises of each of the players, and adding randomness, which is common, make the problem much, much more complicated. As I said, this measure that I could freeze as deterministic measure before, now they're going to become as measured value stochastic processes, and now we're going to fix them and try to find a fixed point in such a huge space. So this is a problem which is very difficult. Pierre-Louis is working on it. I'm working on it with the collaborator, and we have some significant result, but this is very, very challenging and difficult mathematically. But I think practically, I think this is extremely important. Another set of application which I think was introduced by Minnie Huang, Canada also, who was here at the conference in August, is major and minor player, where you may imagine that you have, if you want to talk about economics, you have a few major banks like Morgan Stanley, JP Morgan, Goldman Sachs, etc., and a bunch of a lot of small banks. And we may imagine that in the dynamics, the change, whatever the behavior of the large bank, they don't care at all about the individual bank. They may worry about the average of the small banks, but not the individual bank. But on the other hand, the behavior, the dynamics of the little bank, they may, on the other hand, depend upon the behavior of the large bank. That creates some sort of dissymmetry in the problem. That's not the fact that you're breaking the symmetry, which is difficult. This is essentially the same level of difficulty as the random environment problem. Okay, and I'm going to finish because I really want to finish on time. In my old age, I decided that this is something that I will do. Never go over time. Is that there are a certain number of application of mean field game to let's say finance. Order book models. I don't think they've been successful enough to bring them to the level where you can solve within these models an optimal execution problem. That's certainly not the case. But as I said, major minor player. again, these has been solved by Huang, Bensusan, and what is interesting is that I believe that Huang didn't solve the right problem, even though, he brought the problem to the attention of many people. Bensusan and his collaborator, I think, understood the right formulation of the problem, but I still believe they didn't solve it properly. And again, the solutions are only in the linear quadratic case, which is pathetically specific. I am now working myself on something which I find extremely exciting, which is something that I learned from a colleague, Sannikov, namely that when you have a principal agent contracting with the principal contracting with the agent, and he wants the agent to behave in a certain way. But so all these models are one agent and one principal. So let's imagine that I am one agent and I have a franchise of owner. I'm Mr. McDonald, and I have all the franchise people owning a McDonald, and I want them to behave a specific way. So I'm going to give them a contract, and I want this contract to force them, basically, if they act optimally. So they're going to compete, they're going to solve a game, and I want this, in a sense, the second part of the problem to be a mean field game. Or, and that was my original motivation, you may imagine that I'm the regulator in Europe, and I want my companies to produce electricity but do not emit too much CO2, and I want to give them a contract. I want to design an emission trading system so that while they optimize whatever they optimize, they will behave the way I expected them to behave. So I think these problems, I don't know of anything that is written on this, but these are pretty interesting problem. And of course, what I will not try to sell here, but what was really driving me insane and extremely excited is that there are an enormous amount of mathematical problem, mathematical conjecture, mathematical theorem to be proven that are just in your face when you start to looking at this problem, and they've not been studied before. For example, let's look at the McInverse equation. They have been written everywhere, used by physicists for many years. People have done stochastic control for years. The stochastic control of McInverse of dynamics have never been looked at, as far as I understand. Now, I don't want to write a paper for the sake of writing a paper and adding one more publication to the insanity that is out there. But this comes naturally, and this corresponds to a certain type of equilibrium, which I thought for many months, for a couple of years, I thought that was the same thing as the mean field gain problem. And actually, I talked to some of the big guys in the field, and they thought also that was the same thing. But it is not, okay? It is not. Stochastic PDEs, which appear here all over the place, are of a very special type. And even the simplest, if you're in Europe or in China, that all probability is about BSD, backward stochastic differential equation. You cannot publish a paper without putting a BSD somewhere. But BSD, where the coefficient depend upon the distribution, were not really studied. And again, I would hate people to do that for their own sake, but here they appear naturally in your face. No one is calling me except the time. So I'm done. Thank you.